Good morning. Um, we are moving on now into chapter 40. Chapter 39, we took a look at the quantum physics of atoms, and in particular, we were looking at electron quantum states in atoms. Now we're going to move on and take a look at combinations of atoms, and they're going to fall into the categories of molecules with a well-defined molecular formula. And then we'll also look at kind of solids. Solids here meaning, a collection of atoms. So in a block of iron or a block of copper, for example, there's no set molecular formula. Any number of metal atoms can join together and form a block of some type of metal. So anyway, that's what this chapter is looking at. We're going to start off by looking at molecules. And the simplest molecules, we're going to be looking at things like the hydrogen molecule, H2. But a couple things here. It says a molecule, two or more atoms strongly held together to function as a unit. It talks about chemical bonds here. Now, the slides here, and the textbook to some extent too, classifies these bonds as covalent or ionic. But let's take a closer look at those categories. So it's saying here in a hydrogen molecule. So a hydrogen molecule would consist of, well, two hydrogens. So the formula is H2. What that means is that we've got two protons, two nuclei, and two electrons. And as those protons, they've got those designated here as being red, the nucleus, and then the electron is represented as some kind of a distribution. So we're thinking back in terms of wave functions, which we saw for those electrons back in chapter 39. And as you bring two hydrogen atoms closer together, what we're seeing here is there's different ways that the electrons could fall into patterns around the nucleus. Now the pattern we have right here is actually a situation where the electrons have fallen into a quantum state where there's a node down the middle. There's a decrease in probability, and that won't hold the two nuclei together. In order to hold the two nuclei together, in order to form a chemical bond, what we want to have happen is to have two electrons fall into some type of new hybrid molecular quantum state, molecular wave function, that builds up negative probability between the two nuclei. That's basically what happens in chemical bonding. 99.9% of the chemical bonds correspond to a pair of electrons showing up in between nuclei. All right. There's some more complexity to that, but now I noticed in the slide too it says that if the spins are aligned, that's not really what's going on here. And anyway, that's not important for us, as it is the fact that this particular wave function isn't going to hold the nuclei together. It's not going to form a chemical bond. Here is the alternate. So there's two different ways that the wave functions can combine. If we take the wave function for the electron in atom number 1, wave function for the atom electron in atom number 2, when we combine those two wave functions together, there's a way in which the wave functions overlap in the middle and reinforce, and that's what this is showing. And then there's a way that the wave functions cancel each other out in the middle. So this is referred to as anti-bonding, and this is referred to as bonding. And spin turns out to be a separate issue. So I'm not sure why they are... anyway, now here's another diagram representing the same sort of thing. And so when we start looking at chemical bonds, bonds forming between nuclei inside atoms, they range from what we consider to be covalent, polar covalent. Now this ionic term, it's a little misleading, I always feel. We got to be careful about exactly what ionic means. In in molecules, in ionic molecules, it's just an extreme case of polar covalence. So let's take a look at that. So here's this H2 molecule that has formed, and we said we want a molecular wave function, a bonding wave function, in which we can get a pair of electrons. Now the reason it's a pair is because you can have spin up or spin down. So spin up, spin down enables us to have a pair of electrons going into that bonding state. Now, since hydrogen and hydrogen, they're identical, they're completely symmetric, the wave functions that we come up with are going to have the electrons symmetrically placed between the two nuclei. They don't spend more time over by one nucleus than the other. For a chemical bond as in H2, it's going to be perfectly covalent, equally shared electrons. And again, that means we've got a pair of electrons in some type of a molecular wave function, and that wave function has a buildup of electrons between the two nuclei, holding the two nuclei together, forming the chemical bond. Now, to represent that, so the H2 molecule could be represented this way. Here is an H2, or here's a hydrogen atom with an electron in a 1s state. Here's another hydrogen atom with the electron in a 1s state. When we bring those two wave functions together, they can come together in a way where they overlap. I can add the two wave functions together. Or they can come together in a way where they cancel out. We actually take one wave function and the second wave function, and instead of adding the effects of the two wave functions, we take the difference. And that reduces the buildup of electrons between the two nuclei, and that gives us an alternate linear combination. So mathematically, these are actually linear combinations of the atomic wave functions that we looked at in chapter 39. So since hydrogen, each hydrogen brings in one electron each, those two electrons can drop into the lower energy bonding state. Now, flipping the spin on the electron is not a big deal. So regardless of how the spins were oriented to start with, in the bonding state, we are going to have both the electrons set up, spin down. What the previous slide seems to be saying is one of the electrons gets stuck up here. It's not a big deal, though, to get that electron and bring it back down. Now, that would be one electron in two different wave functions. Anyway, now let's compare the bond that forms in H2 with one of the bonds that forms in H2O, the water molecule. And in a water molecule, what happens is each of the hydrogens is attached to the central oxygen. Now, a wave function forms. In this case, so there's a wave function that forms, and we get a pair of electrons spin up, spin down, going into that bonding wave function. And see, we're getting plenty of probability, plenty of wave function amplitude built up between the hydrogen nucleus and the oxygen nucleus. But what happens in this case is because of the wave pattern of the electrons, that molecular orbital that forms is going to be shifted towards the oxygen. This is a result of the wave functions meeting the boundary conditions for the Schrödinger equation that we looked at in chapter 39. So we refer to this as different elements are more electronegative. And being more electronegative means that the number of electrons you have allows for additional electrons to come into some molecular wave functions and be drawn closer to that particular nucleus. Okay, so we'll save more detail of this for chemistry classes, or probably more detail for physical chemistry courses, upper division. But that's kind of the basic idea of how these chemical bonds are formed. Now, looking at the H2O bonding in just a little bit more detail. So here is a hydrogen coming in, and it's got one electron in a 1s state. Now the oxygen coming in is going to be is going to have 8 electrons with it. So if I look at the configuration of electrons in an isolated hydrogen and an isolated oxygen, these are the electron configurations we've got. Now in the oxygen, there's a 1s pair of electrons that form a core. We feel, when we list something as a core electron, we say that when it forms chemical bonds, these electrons aren't really disturbed very much at all. They're already so closely attached with the nucleus, the presence of another nucleus doesn't have that much of an effect on them. But these outer electrons can reconfigure themselves. So electrons don't have to stay, when they're forming chemical bonds, the electrons are not going to be in atomic wave functions. Those wave functions we looked back in chapter 39, those applied for individual atoms, electrons in individual atoms. What we can do mathematically is we can take these, in this case, these two S states and these two P states, and what we can do is we can mathematically combine them in a way where the electrons are able to more efficiently, let's say lower in energy, they're going to be able to form configurations that are lower in energy. So when it comes down to forming chemical bonds, the formation of a chemical bond releases energy, and then you're stuck. So you can think of it that way. When you form something more stable, the leftover energy radiates away, and then you're kind of stuck there until some more energy comes in from some source. So that's kind of the story of why are molecules, the molecules that are very stable, why are they very stable? Because they found a configuration of the electron wave functions relative to the nuclei that lowers the energy as much as possible. And disassembling those molecules is going to require energy to come back in. All right. So these 2s and 2p atomic orbitals are able to reconfigure themselves into a tetrahedral pattern. So rather than having these spherical 2s's and these lobe-shaped 2p's, what we can get is 4 symmetrically placed lobes, and this gets referred to as sp3 hybridization. So that forms 4, again, symmetrically placed patterns for the electrons. Now, if I look at these 4 possible sets of electrons, I see this is already full, spin up, spin down, this is full, spin up, spin down. But oxygen does have these 2 remaining unpaired electrons. And those unpaired electrons are available to form chemical bonds with hydrogen. The paired electrons are going to also end up filling different regions of space. So in that tetrahedral pattern, of the 4 different directions, the 4 different regions of space being filled, 2 of those tetrahedral directions are filled with pairs of electrons. The other 2 are also filled with pairs of electrons, but at the other side of those electrons are nuclei. The hydrogen nuclei are attached at the other end. Okay, and when we say this is tetrahedral, the 4 directions we've defined are pointing to the corners of a tetrahedron. All right, so anyway, that's kind of taking what we had done in chapter 39 and seeing how we can combine those different atomic orbitals to create new patterns of orbitals. So they don't have to look, in fact they're not going to look the same as they did in the atomic cases. And we get these hybridizations. We get these new patterns of molecular orbitals. Now here we're looking at sodium chloride. And we have to be really careful about what we mean by sodium chloride here. Sodium chloride is typically listed as an ionic bond. And certainly if you take solid sodium chloride, a crystal of sodium chloride, and drop it into water, it dissolves. So when it dissolves, you're separating out these sodium and chlorine atoms, or ions, in the water. Now, if we bring it together and make a block of sodium chloride, then it's not just a molecule, there's a crystal structure, it's an extended crystal structure. So if all we're looking at is one molecule of sodium chloride, then that involves one sodium atom and one chlorine atom, and that's it. That's all that we've got in this particular molecule. So now what they're showing here is there is a pair of electrons, once again, there's a pair of electrons, one coming from the sodium, one coming from the chlorine, that forms a pair of electrons in the region between the two nuclei. In sodium chloride, the distribution is shifted even more than in a polar configuration. So if we went back to here, so we've got covalent bonds where the electron pair is shared equally, and then something like H2O, where the oxygen, the pair of electrons is shifted so it spends more time near the oxygen, that generates a negative charge at that end of the molecule. And now what we're seeing is it's really shifted towards this, in this case, the chlorine, and the chlorine becomes pretty negative. Now, it's not going to be one full electron that completely shifted over. It's going to be something less than that. Let's take a look at the next slide. And this is probably more detailed than we're going to worry about. Here is a diagram of the water. So this is a pretty useful diagram for water. What we're seeing is that we've got electron density in the region of the nuclei, especially the core electron. And then we've got electron density that gets built up between the nuclei and forms the chemical bond. So that's holding things together. So this is polar. Now just very quickly, just a reminder, charges that match repel, charges that are opposite attract each other. And so we've got the two positive charges from the two nuclei involved in a chemical bond. And then what we have is a more complicated set of repulsions between the electrons in the two molecules. So we've got repulsions. The two nuclei are both positive, they repel. The electrons repel. And then the electrons are drawn to both nuclei. Whether the electrons are in atom 1 or atom 2, they are feeling the effects of both nuclei. And so to calculate the total chemical potential energy, we have to take into account all of those contributions, the repulsive energies as well as the attractive energies. Now going back, this is showing a hydrogen molecule, it says, but it could be anything. Or it could be many different types of chemical bonds, let's say. So in the hydrogen system, what happens is, this R is saying how close the two atoms are. So you could imagine starting with two hydrogen atoms, and you allow them just to come closer and closer and closer, a little bit at a time. And what happens is, as you become closer, we have to ask, okay, what happens with the overall potential energy, or the overall energy rather? Does it go up or does it go down? And what we find is when we bring two hydrogen atoms closer and closer together, the overall energy begins to drop off. So there's no barrier to the formation of H2. Two atoms come together, there's nothing that ever gets in their way, they just prefer getting closer and closer until they hit a lowest energy state. Now, the lowest energy state is characterized by an attractive force. Overall, the electromagnetic forces between those protons and electrons, if we add them all together, it's stable. It's released a lot of energy. And if it collapses more, it's going to be even more stable. So electromagnetics alone would not prevent the collapse of this molecule into a smaller and smaller system. What does happen is quantum mechanics steps in. So the energies in particular that are preventing the collapse of this H2 molecule, they're calling this a repulsive force, and saying that the overall here the force is attractive, but when we get to here the force is repulsive. What we should say is, as the electrons get packed into smaller and smaller regions, that requires the electrons to have more and more kinetic energy. So it's actually the introduction of the kinetic energy of the electrons that produces this barrier towards the atom collapsing. So again, what's happening here, the axes, the vertical axis is, they're calling it potential energy. I'm going to say it's total energy. It's including the potential energy from the electromagnetic effects, plus and plus, plus and minus, minus and plus, minus and minus. And, but it's also including the kinetic energies of the electrons and the nuclei. The nuclei turn out not to have very much kinetic energy, but the kinetic energy of the electrons goes up rapidly as we try and push the electrons into smaller and smaller regions. So I do like the phrasing they have here. What they say is, if the atoms, as the atoms get closer together, the electrons are too squeezed. Okay, so you can imagine the electrons going, we're too squeezed, we're too squeezed. So what too squeezed means here is the kinetic energies are going up, and that's preventing the collapse from continuing. So it's totally an energy calculation. Comes from solving the Schrodinger equation and finding out where the stable states are going to be located. Okay. So it's not that at some point, because I had this explanation given to me so many times in school, that at some point, instead of the nuclei and electrons attracting each other, they start repelling each other. But it's really these quantum effects that come into play. All right, here's an alternate profile. This says, and again, if we're forming the chemical bond, rather than starting at the zero end of this, we start out here where the atoms are far, far, far away from each other. And here it's saying that in many, many chemical reactions, fortunately, there's an activation energy that you have to get past. So in the hydrogen case, we said as the hydrogen atoms get closer and closer, there is no point. There is no activation energy that we have to go past. Put a bunch of hydrogen atoms together, they will spontaneously form hydrogen molecules. Here, there's an activation energy that you have to get past. So this prevents everything from, all the chemical reaction from immediately running on many, many materials. You would have to get past an activation energy before the chemical bond would form, before you find that minimization state. Now they've got a more detailed example here. And this is the sodium chloride bond. And again, what we have to remember here is it's one molecule of sodium chloride. It's not a crystal of sodium chloride that we're looking at. So what it says is this. It says here's one way to think about that activation energy. So they're thinking it as a two-step process. Here's sodium, here's chlorine. They've actually modeled this as an electron from sodium leaves and goes over and attaches itself to chlorine. Okay, and so what they've shown is that process, the energy required to remove the electron from sodium and then place it on the chlorine, gives us a net effect of 1.53 eV. So, and at that point, these are no longer atoms. Well, they're atoms, they're ions, I guess. So the sodium is now sodium plus and the chlorine is now chlorine minus, whereas before they started as two separate atoms. And then once you've got these two ions, then they model this as if it's a couple of point charges being drawn towards each other. Now to me that seems like quite a simplification, treating the atoms as point charges, but what we find is that it actually does pretty well in terms of predicting what the energies would be. So it's pretty good at predicting what some of the binding energy would be for this particular molecule. So I did this. I went ahead and there was a problem on that previous slide saying calculate the separation distance at which the potential of the sodium and chloride ions drops to 0. Measured value is 0.94. So it's so what we've done here is we've said, okay, here's the process. We're going to start with 2 atoms, a sodium and a chlorine atom. We're going to first of all move the electrons, switch those, move one of the electrons off the sodium onto the chlorine, and then let those 2 ions come together to form a molecule. Now I've taken a look at the energy profile that they have here, and what they're asking is at what point would the potential energy in the system be equal to this measured value of 1.53 eV. So what they're saying is that this is the potential energy associated with that particular state. Now, if we go in and measure this, if we say that we're going to set the potential energy equal to Q1 Q2 over R. Now that's a formula back from physics 4b. So that's just the potential energy for 2 point charges. And that's how we're going to be treating these sodium and chlorine ions. Now the point charges, each of those we're going to treat as if they have a charge of E. So since we've moved 1 electron off of the sodium now has 1 full charge of E plus E, and the chlorine has 1 charge minus E. And so there's a shortcut here too. If you take Ke squared and put all those values in, and then convert that into EV nanometers, that combination of Ke squared it's 1.44. That's a handy number. We're going to see that in this chapter. We'll see that when we get into a nuclei. The KEE as 1.44 can be kind of a shortcut. The KE combination shows up in a lot of formulas. So we can take the 1.44 eV, divide that by 1.53 eV, and that predicts separation distance of 0.941 nanometers, or 941 picometers. I'm sorry, that's an erasure. It's not a decimal. It's an erasure that I ended up with. So that's what we're getting for this equilibrium distance. Now, in the other part of the problem, they tell us that the sodium and chlorine eventually end up the sodium and chlorine eventually end up with a bond length of 0.24 nanometers. So they say that's the equilibrium distance between the 2 nuclei when the molecule forms. So this is kind of carrying out the calculation the other way around. What it's saying is if this is the equilibrium separation, we can calculate how much potential energy due to electromagnetic effects is present at that distance. So this time, again, it's the same formula, but I'm solving for potential energy. And it says actually, the potential energy has dropped all the way to negative 6.0 eV at that distance. So at that distance, we're at negative 6.0 eV. Now, the bond energy that they tell us about here, or the bond energy rather that they show on the diagram, does not include all of that effect. So the bonding that's taking place there, it's not, there's an attractive force that's taking place, but there's also, we're beginning to see the effects of the electrons pushing against each other. So in any case, using these formulas where we say U is equal to Ke squared over R is kind of a pretty simple model. I always feel like, again, chemical bonding is more complicated than just working from kind of that that's something that gives us a reasonable kind of order of magnitude calculation. All right, here's a different sort of energy profile. This is one that's listed for biological systems. You may have heard of ATP and ADP as molecules inside cells. The ATP has 3 phosphate units attached to an adenine or adenosine, and the ADP, one of those phosphates has been removed. And it's actually a molecule that gets used for energy storage. And this molecule has an interesting profile in that it's got an activation energy. Once you get over that, there's a local minimum. But the local minimum is still much higher in energy. So it says that with a little bit of activation energy in the opposite direction, we can actually release a lot of energy. So a lot of times these, the phosphate bonds in ATP and ADP are referred to as energy-rich bonds, and so it just takes a little bit of a dip in the energy here to make the molecule stable. Doesn't take so much activation energy, so it's not too difficult for an enzyme to come in and allow that phosphate group to come off. And then when the enzyme comes in, overcomes that very modest energy barrier, there's a large release of energy. Now here's one more model. I know we're looking at a lot of this modeling stuff in chemical bonds. It says here's another way we could think about the energy. And again, it's not potential energy here unless you're thinking of the electron kinetic energies as being included. Anyway, this formula right here, that's the electromagnetic formula we have been using. The formula over here, B over R to the 6, that's just a function that's being used to represent a really steep curve. So what they're saying is this. Let's rewrite this. I guess I followed their lead. I wrote this as a potential energy, but again, I want to think of it as including kinetic energies of the electrons. So it's more than just the potential energy. Here's an attractive force. That's our electromagnetic force attracting charged objects. This is a repulsion, and it's a large repulsion. It's 1 over R to the 6. So it says that this repulsion isn't very large until the two nuclei get pretty close together, and then the repulsion becomes pretty extreme. The energy rises rapidly as the atom gets closer together in this direction. Now, for this particular model, what they did is they just, in this example, if you look on the slide, they gave us a value of B. They didn't say where this came from. So when chemists or physical chemists take a look and model these kinds of reactions, they're coming up with what power of R should we use for the repulsion. Different values of R get used, and then they're coming up with different constants. So again, this is not coming from necessarily fundamental principles. It's just finding out what kind of mathematical functions match our observed properties for these chemical bonds. So what we can do, we can play around with this a little bit. This tells us how much energy there is as a function of R. What we would like to do is, given that model, where does the energy minimize? At what value of R is the equilibrium to be found? So by minimizing the energy, we can find out what the bond length is, and that's what the R naught's keeping track of. So du dr, start from there. What I'm going to do is just take a derivative. And so I've taken a derivative, and that first term becomes ke squared over R squared. That second term becomes, that's a 6, minus 6, you know, it looks like G, minus 6b over R to the 7. And we're going to set that derivative equal to 0 because that's how you find mins and maxes in functions. And that condition becomes this. And then we can solve for R naught. So what is the value of R that minimizes the energy function? And solving this equation, now the ke squared, I kind of have an idea where that's coming from. The b, remember, just came from the modeling. So somebody came up with this value of B by looking at different molecules. And for this particular example, it gives us an equilibrium separation of 121 picometers. And that's it. That matches the lengths of many chemical bonds. So the next thing we could do then is, once we know what the R naught value is that minimizes this function, what we can do then is take that R naught and put it back in. So if I plug that back into the formula, that will tell me at the equilibrium location what is the energy given by. And so I plug this in, and as always, check my numbers, but I ended up with minus 9.91 EV. So it's saying, hey, that's the bond energy. So if this is reliably modeling the chemical bond properties, then this allowed us, this minimization, taking a derivative, allowed us to find out what the equilibrium separation would be. That becomes the bond length. And then we can plug that number back in and find out the value of the energy function for that distance. Okay. All right, now there's other interactions going on in molecules. These are being classified as weak chemical bonds, so van der Waals forces, London dispersion forces. You get these different effects taking place because even once the chemical bond has formed, there's still going to be leftover electromagnetic effects going on. So here's an example taken actually out of DNA. So let's take a look at the DNA molecule. So here we go. Here's a double helix of DNA, and you see all the A's and T's and G's and C's in there. So here's an example. Here's cytosine and guanine, and you can see what happens here is it's not full-blown chemical bonds that get formed. What happens is, because the electron density is being drawn away from that hydrogen back towards the nitrogen, and in this hydrogen back towards that nitrogen, and in this hydrogen back towards that nitrogen, and the oxygens are tending to draw electrons towards them. So this is all coming back to that polar nature of covalent bonds. So, you know, if this is molecular biology or biochemistry, it's pretty much all being done with hydrogen, nitrogen, carbon, oxygen. Those are kind of the big four, with maybe some, you know, phosphorus thrown in. And so the electronegativities of these different elements become very important. So you build up little residual charges, plus and minus. And so in the DNA, the DNA two strands are held together not with what we would think of as full-blown covalent bonds, but as kind of these leftover effects. And so that's what allows the DNA strands to be unzipped and then to zip back together. Each of these individual bases within DNA, the bases referring to A, T, G's, and C's, they have a small potential energy associated with their attraction. So that's what they're looking at here. And it's saying that this particular interaction corresponds to maybe, you know, a few tenths of an EV, something like that. So let's do a calculation here. Now again, it's an estimate. What they're assuming in this example is that the polar nature of this carbon-oxygen double bond, the polar nature on that produces effectively not a full electron. So it's not like a full electron got up and changed places, but the polar nature of the bond creates the effect of the carbon picking up, or the oxygen rather, picking up 0.42 electrons. So the carbon becomes a little bit positive and the oxygen a little bit negative, and the number they're assigning to that is like, it's the equivalent of 0.42 electrons of charge, fundamental charges, because of the electron shift. In the hydrogen-nitrogen bond, that polarization creates an effect that's equivalent to a 0.19. So what they're saying now is what we could do is look at the combination of interactions between, well, the carbon and the hydrogen, the carbon and the nitrogen, the oxygen and the hydrogen, the oxygen and the nitrogen, and calculate how much energy there is in those charges. So treat them as if they're point charges with these values, not a full fundamental charge, but just a portion. All right, so I wrote that up. I said, okay, here we go. What we've got is we've got charges plus and minus here, and charges plus and minus here. Now those are dipoles, so we could go through and calculate the energy of interaction for two dipoles. And so here is the carbon and the oxygen on this side, and we're assigning this plus Q1 and minus Q1, and then this is plus Q2 and minus Q2, and this side was 0.42, and the other side was 0.19. Now the general formula for this would be electromagnetic force constant times the two charges divided by the distance between them. So I took a look at that diagram, and I was able to see the distance between these two charges, 0.12 nanometers. The distance here is 0.10 nanometers, the distance here is 0.19. And so for each of these four possible pairings, I went through and calculated how much potential energy there would be due to the presence of those, kind of that leftover amount of charge. And what I found was this. What I found was, as expected, the plus carbon here and the plus hydrogen here, they're repelling each other, as are the negative oxygen and the negative nitrogen. And here's the amount of repulsive potential energy. Those came in at 0.371 and 0.396. And if you take a look at the distances here, I had to keep track of what the distances would be for each of those combinations. All right, so I've got repulsion between these two and repulsion between these. Now what we want to do is look at the attraction. I'm going to get an attraction here, and that's going to be the dominant attraction because that's the one that's really close. And then these are also going to provide a little bit of attraction. So the carbon and the nitrogen, now those are the ones at the ends. Those actually provided a fair amount of attraction, negative 2.80 eV. And then these two, the ones that were really close, the oxygen and the hydrogen, kind of this polar hydrogen bonding effect, that provided the biggest boost to the attractive effect. So what it says is that the two repulsion energies were offset, more than offset, by the two attractive potential energies. Everyone was calculated by using KQ over R. The total turned out to be about 1/10 of an eV. So kind of in the range that they were suggesting. Now, you might be thinking, well, wait a minute, didn't we leave out the carbon, oxygen, and the hydrogen, nitrogen energies? And those have already been taken into account due to the formation of those chemical bonds. So those are covalent bond energies that are already in place. What we're specifically looking at is as the DNA zips together or it unzips, how much energy is released when it comes together. And it says this one hydrogen bonding example, this one dipole example, would release 0.118 eV when it comes together. And then how much energy would it take to unzip the DNA? And to unzip this particular attraction would be 0.118 eV. I'd need that energy back in order to unzip that particular bond within the DNA. All right, and there it is. So here's a picture of protein synthesis. If you look at all kinds of biological systems, biological molecules, a lot of stuff gets done with these dipole-dipole interactions. So there's enough, it doesn't form a covalent bond with 5 or 6 or 7 or 10 eV. It forms these very small hydrogen bonds or dipole bonds to maybe a tenth of an eV instead. So the bonds are enough to draw the molecules together, but it's also a little enough that the molecules can separate easily.